Okay, on page 111 of your EGM90 lecture notes, in the transonic section of the course where we've just looked at correction similarity rules and then moving on to correction factors that we can apply to take into account compressibility effects in flows above about Mach 0.3. There's this simple little example which I'll go through with you just to give you an idea of practically how you can make use of things like this Prandtl-Glauert rule that we've discussed. So in section 3.5, which is an exercises section, there's a few questions. I won't do them all. We'll just look at number 1 and then it should give you an idea of how you do the rest. So question 1 says, we can approximate the F-15 wing as a thin wing of triangular planform. The planform area is 28 meters squared and the leading edge sweep angle is 45 degrees. The aerodynamic characteristics of the wing is required at a flight Mach number of m infinity 0.53. So we're significantly above Mach 0.3, this rule of thumb we use about whether we need to take into account compressibility effects. The designer has access to a low speed wind tunnel, and I think the inference here is that low speed is meaning below Mach 0.3, so we can assume that the flow in the wind tunnel is incompressible. Describe a wing shape that could be tested in this tunnel to provide the necessary information, and describe how, and then the question jumps down past this figure, how the required values could be obtained from the experimental observations. So we've got a, this is question 1 of exercises 3.5. So we're going to assume that we've got this wing. It's a roughly triangular planform. The wing area is 28 meters squared. The leading edge sweep, we'll call it lambda, is 45 degrees. It gives you an idea of the scale of the real aircraft. We've got oncoming free stream flow at net Mach number of 0.53, and we want to learn about the aerodynamic characteristics of this wing at that Mach number, but in a wind tunnel. So well, let's quickly jump across and have a look at the formula sheet that you have. I'm just going to bring this up on my screen. And yeah, we're already on the right page. So there's this section in the formula sheet, 2D compressible inviscid flow. There's the small perturbation equation, and then the correction factor rules, Gothard's rule and the Prandtl-Glauert rule. Now there's no right or wrong one you can use. Well, there are some wrong ones you could use. And of course, in this case, both the real and the corrected flows are subsonic. We're assuming that Mach 0.53 is below the critical Mach number, because, as we discussed in lectures, these rules only apply in the subsonic case below the critical Mach number. So it's going to be the subsonic, one of the subsonic rules we're going to be choosing from, and we could choose to use either Gothard's rule or one of the Prandtl-Glauert rules. And I'm going to just show you how this works if we choose this first one of the Prandtl-Glauert rules here. This is probably the simplest of them, as we'll see in just a moment. So this tells us that the Cp, the pressure coefficient at a point on this wing at a Mach number 1, on a wing of thickness coefficient tau 1 at an angle of attack alpha 1, is equal to the ratio of these compressibility factors, which are defined over here, for a wing where you're measuring the Cp at Mach 2, where the thickness of the wing is the same as the other one, the original wing, tau 1, and at the same angle of attack, alpha 1. Okay, so you're not actually, in this rule, you're not going to be changing the shape of the wing at all. Okay, the shape stays the same, the thickness to chord ratio stays the same, and the angle of attack at which you're going to be comparing the CPs stays the same. So it's pretty easy, really. So how do we practically apply that? In fact, I'm going to skip back to my notes. So what we will do is assume that the subscript 1 in the PG rule, condition subscript 1, is the real case. So this is the real F-15, full scale, flying at Mach 0.53. Condition 2 is the wind tunnel. Now here we can assume that the Mach number at condition 2 is 0. Now, as we mentioned in the lecture, this doesn't mean when we talk about a Mach number of 0, what we're not saying is that the wind tunnel isn't on, there's no flow over the wing. What we're saying is the Mach number is so small, it's less than 0.3, much less than 1, that the flow is incompressible. So often when you hear this Mach 0, what you're actually saying is the flow is incompressible. So let's point that out there, i.e. incompressible. The question is, if we're running a wind tunnel where the flow is incompressible but the real case is in a compressible flow of Mach 0.53, what correction factor do we need to apply? Well, let's first of all compute our beta 1 and beta 2 compressibility correction factors. So this is going to be 1 minus m1 squared, all square rooted, which is 1 minus 0.53 squared, which is, I worked this out earlier, 0.848. Beta 2, of course, where m2 is 0, is simply 1. So Prandtl-Glauert tells us that the CP at m1, tau 1, alpha 1 is equal to beta 2 over beta 1 times the CP at m2, but the same thickness ratio, same angle of attack. Okay. And what this is telling us, because remember, condition 1, Mach number 1 is the real case, so what I'm going to say is this is the CP for the real aircraft is going to be equal to beta 2, which is 1 over 0.848 times the CP at Mach 2, which is the wind tunnel case. So I'm going to call this wind tunnel. So CP real is equal to 1 over 0.848, which is 1.18 times CP for the wind tunnel. So that's the first observation we can draw. So if, for example, because the question asks experimentally how would you deal with this, so for example if you had a wind tunnel model and across the surface of this wing you had pressure tappings linked to pressure transducers where you are measuring the pressure and converting that into the non-dimensional pressure coefficient Cp on your wing in the wind tunnel, you would expect that the real measurements you would get on the actual aircraft would be 1.18 times what you're measuring in the wind tunnel. If, for example, you were measuring on a force balance the lift and drag coefficients, well, of course, lift and drag are just integrals, and in this case we're ignoring skin friction, so we're going to ignore the skin friction effects in this analysis. They're simply integrals of Cp, or pressure, across the surface of the wing. So similarly, so you can put Cl real be equal to 1.18 times the Cl value in the wind tunnel. I'm going to scroll down if I can. And similarly CD real would be 1.18 times the CD in the wind tunnel. Now, and this is assuming the wing is exactly the same shape, size, and for a given angle of attack. So really what I should say, to be very thorough here, what I should really say is that the CL as a function of alpha on the real wing is going to be 1.18 times the CL as a function of the same alpha in the wind tunnel. Practically speaking, it's unlikely the wind tunnel that we have access to is going to be big enough to fit a 28 metre squared F-15 wing into it. There are wind tunnels that exist that are that big, but it's unlikely that that's the wind tunnel we're using, so we're going to have to scale it. Now, this is a little aside, really, but I just thought I'd draw your attention to this and the challenges, of course, of doing wind tunnel modelling. But what we're trying to achieve is that the Reynolds number of the real world is equal to the Reynolds number of the wind tunnel. The definition of Reynolds number, of course, is rho v real times, let's use our reference length as the chord, so the chord real over the dynamic viscosity of the air should be equal to rho times v of the wind tunnel times c wind tunnel. Now let's say to fit this into our tunnel we need to scale the model down by a linear factor of 10. Well, that would make our wind tunnel model have a reference length of c real over 10 over mu. Now, unless we can do something clever like vary the density of the air in the wind tunnel, or remember using Sutherland's law by changing the temperature of the air to change the viscosity of the air. Let's assume we don't have the capability to do that, so our rho in the real world is the same as rho in the tunnel. Mu in the real world is equal to mu in the tunnel. You can cancel the c and the c real. What this tells us is that what we would need to do for a 1/10 scale wind tunnel model to match the Reynolds number is run at 10 times v real. The problem, of course, is that this is a low-speed wind tunnel, so we're not going to be able to do that. So you quickly see how difficult it is in practical cases to do both kind of Mach matching, even if you're applying compressibility corrections, and get the Reynolds number right. So in this case, you probably just have to accept that your Reynolds number is not going to match. So that just gives you a little idea of how you can use those correction factors. Have a go at using one or the other one, either Gothard's rule or the alternative version of the Prandtl-Glauert rule, because there are different ways of doing this. So yeah, have a little play around with that.